Hello everyone. Oh, this video I'm going to show you an example for energy conservation calculation. Let us see the problem. Okay, it's an inclined surface problem. Suppose you have a crate, which is 3 kilograms. You slide down a ramp. Initially, this crate, its velocity is 0. You slide down from the crate, and the distance of the ramp, yeah, I think it's 1.0 meter. And then you want to calculate what's the final velocity when the crate hit the ground, and give you the geometry information. Okay, you have lots of geometry information. That's the first. Use the energy method to determine the speed of the crate at the bottom of the ramp. And the second question is the how does the crate stay on the horizontal floor if it continues to experience a friction force of the magnitude 5.0 Newton? Yeah, the second question is when this crate hit this position, it will continue to slide on the horizontal surface and experience the same friction force. The friction force is also 5 Newton. And how long will it slide on the horizontal surface? And in this problem, I'm just going to show you the calculation of first one. Okay, the first problem and second problem, I think you can solve it yourself. Second problem is as easy as the first one. Okay, so I just demonstrate the A problem, and the second problem you can solve by yourself. And he said use the energy method. Okay, so it's a typical energy conservation calculation. Okay. Sorry, that's wrong. It's here. It is. Okay, here's a setup of this problem. Okay, so let's us energy conservation. Okay, energy conservation. Remember what's the equation for the energy conservation? Okay, why it's still not change the color? Why? What? What? Why didn't change the color? Okay. Okay, equation for energy conservation is delta K plus delta U equal to heat plus work done by the external force. Okay, so in this problem, energy conservation problem, I always say, okay, just analyze your initial state and final state first. Don't jump into conclusion. So, okay, let's start with that's the initial state. Okay, initial state is here, right on top. Okay, and final state. The final state, final start. Okay, so initial state, what's your kinetic energy? What is your potential energy? Okay, final state, what's the kinetic energy? And what's the potential energy? Okay, so let's start initial state here. And the initial state, I say initial state, the crate is at rest. There's no velocity. And no velocity, that means there's no kinetic energy. Because kinetic energy is 1/2 times mass times velocity squared. No velocity means no kinetic energy. And the other thing, what's the potential energy of the system? Okay, potential energy in this method, we have two kinds of potential energy. One is gravitational potential energy, the other is elastic potential energy. So right now in this system, we only have, looks like we don't have any spring, so we only have the gravitational potential energy. And gravitational potential energy is mgh, mass times the acceleration of gravity and times the height. And regarding to the height, it's also we have to define a coordinate. Once again, coordinate. So coordinate. So let's suppose. Okay, this is the y direction. We set the height, the origin of the height 0 point is here. Okay, so mg times h. So mg times h. So if the origin is here, origin of height is here. So initial position, okay, is 0 point meter. higher than the ground. So it's mg 0.5. Okay, what's the final state? Okay, when the crate slide down from the ramp, okay, and finally is a increase. It was the gravitation will make the going down, and gravitation is a force cause the motion change. So when you hit the ground, it must carry certain velocity, and a certain velocity I don't know because that's the question I want to ask. So I don't know the velocity f. So let's just okay. Let's just use VF to represent the final mass n square. And the potential energy, because we hit the ground, we set the potential energy, we set the height origin is here. So at the final state, the height is 0. So it's mg times 0. So that means it's just 0. Okay, that's the kinetic energy and potential energy. And the next thing is there any heat and work done by external force? Let's say, okay, what is Q? Because there's a friction, so we always assume the friction generate heat, and friction is always opposite to your moving directions. Okay, so the friction, what's the work done by the friction? Is a friction force times the distance. Okay, and don't forget the negative value because it generates heat. It released heat, so it's negative sign. Release heat is negative sign. You add the heat is positive sign. Okay, so okay. So what's the value? Okay, and the problem is very nice. He already tell you the friction was 5 Newton, so you don't have to calculate it again. Okay, and the distance. Okay, the distance is from top to down, the top of ramp to the down the ramp, and the question already give you its distance. The distance is 1.0 meters. Okay, 1.0 meter. Okay, and there's no external force done on the system. Okay, so that makes it 0. Okay, so that's almost the whole information. And we put all information in the energy conservation equation. So energy conservation equation is Kf minus Ki and plus Uf plus Ui out of the Uf minus Ui equal to Q plus Wext. Okay, let's put everything in there. So the final state kinetic energy is 1/2 mvf squared. Okay, the minus initial state kinetic energy is 0, and final state potential energy is 0, and initial state potential energy is mg times 0.5, and equals to Q. Q is minus 5 times 1, and is 0. Okay, so mass is 3 and g is 9.8. So we just put a number in there, 1/2 times 3 times Vf squared and minus 3 times 9.8 times 9.5 equal to minus 5. And I think if you use a little algebra work, you will have Vf. What's the value? Vf is okay, Vf is 2.54. Vf is 2.54 as a unit meter per second. Meter per second, because we all use the MKS system, kilogram, Newton. So its unit will be meter per seconds. Okay. Okay, that's the first question. And then the next question is if it's going to move along the horizontal direction after it hit the ground, and how long it will travel on the horizontal surface. Okay, when the object hit the ground, it carries a velocity. Okay, so that means it has also have kinetic energy. And kinetic energy and keep moving on the surface, and this on this surface it still has friction force. Let me draw this. When you move it in horizontal direction here, you move in horizontal direction. At the same time, you know, it also friction force pulling, doing the negative work to slow it down. Okay, the friction force on the horizontal surface still do a negative work. Yeah, frictions. I think because it's moving right opposite, it's right opposite to your moving direction, so it's always doing a negative work. And doing the negative work, that's the pumping out, keep withdrawing your kinetic energy, and then finally it will stop. Okay, so finally it will stop. So actually, because in rooming a horizontal surface, so there is no potential energy change. So yeah, okay, let me finish. Let me finish the second problem. Yeah, at the beginning I said you should finish yourself, but I think because it's very easy, and let's just solve it. Because the final state, because moving on the horizontal surface, it will finally stop. So the final kinetic energy is zero minus initial kinetic energy. Okay, and because moving a horizontal surface, no potential energy difference. Okay, the only thing we have the friction, and friction is negative, and friction force is 5, and the distance I don't know. Okay, no external force. And we have VF here. And putting me in. Okay, we'll finally solve how long you travel. D equal to how long you travel on horizontal surface. 1.95. 1.95 meter. Okay, it's very typical energy conservation problem. Okay, let's only consider friction. Okay, just a little more about friction. Okay, so this is a problem, example problem for energy conservation. I hope you can familiar with this type of calculation. Yeah, with energy conservation problem is much easier and much easier than Newton's second law of motion. Okay, because everything is you'll find everything is scalar, so it's much easier. Calculation is much easier. Okay, as an example, so I just stop video here and see you next video. Bye bye. Bye bye. Oh.